Hey, hello, this is Dr. Muhammad, and this is a new video. I'm going to talk today about the spring motion, and it is considered one of the good application for differential equation in general. So I'm going to talk today about the spring motion or mass spring system. So let's start with the case where that we are having a spring motion or a spring, and it is going to be unforced motion. Unforced motion means that there is no force term or there is no force applied on the system. So let's understand more about this issue. First of all, we need to understand what is how the spring or the mass spring system works and what are the different stages that is going to be analyzed, and where we can find our motion and where we can put and spot the equation that is going to work for us. First of all, let's assume that we have a spring that is attached from above, as you can see. So we have here as if there is fixed wall here, for example, and we have the case where that our spring is unstretched. Unstretched means that there is no masses applied here, there is no forces, nothing, just it is the original case of our spring system. Then after that we can try to put a mass here, which is going to take us to the second level, which is what we call it the static equilibrium case, where that we are going to put a mass. And after putting a mass here, we are going to find that there is a distance d that this spring is going to be stretched with. And at the bottom of this spring, the mass is going to be applied here. We call this static equilibrium. Why it is static equilibrium? Because we have this mass is going to exert force downward in the direction of gravity. We call this mg, which is the gravitational acceleration times the mass of this object. And in the same time, there would be a resisting force that is going to be developed in this spring system. And this force is going to be K, which is the spring stiffness factor, times D, which is the distance already that that this object moves down. Okay? Now we have a minus here. This minus, this is only a sign convention. We are going to say that anything above this object M is going to be minus. Anything goes below this line, dashed line, is going to be positive. This is only a kind of sign convention. So any force that is heading upward, it is minus. Any force that is heading downward, it is positive. Okay? Okay, now still remember, Will, that we didn't do anything, just we put the mass here. At the bottom we put the mass, then we found that there is the spring is being stretched. Okay. Now let's assume that on the bottom of this mass we are going to apply force here. We are going to apply force here. So in this case, if we're going to apply force, which is, I call it F of t, and it is heading downward, so it is positive. When we are going to make this, if the mass here, and we applied the force here, then there is a kind of displacement or movement. This movement will be governed, or it will be a variable. Okay, here it was constant because it is the mass times the gravitational acceleration. It's a constant, and there is equilibrium. We call it static equilibrium position. But here the force is going to be variable. It is going to be changing with time. It is going to be changing with time. This means that we are having variable displacement is going to be applied here. Okay, so this means that we are going to have different displacement based on the time t. Well, in this case, let's assume what are the forces on this object now. We have the external force F of t, which is heading downward, and we are having the spring stiffness force, which is heading upward, so that it's minus, and we have Another term, which is, we call it the damping term, or the damping force. Damping means we found that whenever that there is a mass that is going to move in a medium, there might be a kind of resistance around this object, okay? And we found that this resistance is related to the velocity, y prime. It is not related to y, and it's not related to y double prime, which is the acceleration. It is related to y prime, the velocity. So this is based on experiments. We found that this velocity times a constant called damping coefficient is representing the damping force in a spring mass system. Okay, so now we have different forces. Let's put them together. Okay, let's put them together. Now we have, first of all, we have the elastic force, which is minus ky. We already mentioned about this, minus ky. And we have minus cy prime, which is the damping force. We call it the damping force. And we have the external force term, which is heading downward. It is heading downward. So this is our spring motion equation. Okay, this is our spring motion equation. It describes the motion of our object if it is attached with a spring. Okay, now it's very nice and very good up till now. There is no problem with this. Okay. Now we want to know that the right-hand side of this equation, which is the three forces, elastic force, damping force, external force, the summation of them is going to yield some net force at the end, right? We do not know which one is going to be higher than other or larger than other. So their summation, algebraic summation, is going to give us a value, which is F. Actually, this F, we can put it as my double prime. Why? Why we put it like this? These are the net forces, or these are the forces applied on the object. And the algebraic summation of them is going to give us the net force that is being applied on the object M. So from the Newton law, Newton's second law, we can say that the net forces applied on a mass, okay, is equal to, or the net forces applied on a mass is equal to the mass of the object times its acceleration, right? Mass times acceleration. So based on this, we have my double prime on the left-hand side equals to the right-hand side that we have, which is minus ky minus cy prime plus f of t, the external force. Okay, so now we understood meaning of the spring motion equation. Let's go and further give more details, or give further details for this. This is our equation, and this is the Newton my double prime, the Newton law regarding this issue. We are going to rearrange it to put it in a nicer form. So we are going to divide it by m, all the equation going to be divided by m, and we are going to put this term, putting here in the left hand side, and this term in the left hand side, and put it in a form that's similar to this way. We're going to have something like this, which is y double prime plus c over m y prime plus k over m y equals to 1 over m f of t. Okay, this is what we call it, the spring equation. This is the spring equation. Okay, is it similar to something that we used to solve before? Yes, it is very similar to our ordinary differential equation that we have used before, and it is constant coefficients here, right? And we have c over m, we have k over m, they are going to be constants for us. And we have y double prime, y, and in the right hand side we have a term. So this means that we are dealing with like non-homogeneous differential equation. Yes, it is. It is non-homogeneous differential equation. We have the right hand side is going to be a term, and we have here the left hand side similar to the constant coefficient case for the homogeneous equation. Okay, so we have our differential equation. Now this is one of the most, or we can say, this is why the spring mass system, or the BUB, is considered to be a very good application for what we have been studying for maybe over 1 month now. So now it comes to us that here we have a differential equation that is really representing a motion of an object for a spring mass system, and we are going to use our techniques for the solution of this non-homogeneous equation in order to get and obtain the motion, or to obtain the motion of this object at any point of time. Okay, now let's go to the next case. We are going to have two cases that in order to deal with for our case. The first case, this is the first case, which is the unforced motion. Unforced motion means that the right hand side of the equation is going to be 0. We are going to cancel it. So the left hand side is equal to 0, as if it equals to 0. There is no forces going to be applied on our system. Okay? So the motion is unforced if f of t equal to 0. Now the spring equation is homogeneous, and the characteristic equation has the roots. Do you remember the characteristic equation? You can recall this from the previous videos, okay? So this is a constant coefficient case, and we can get the characteristic equation easily from it. We have trained and we have many examples, and you have solved many assignments regarding this issue. So now our lambda is going to be something similar to this. C, which is the damping coefficient, over 2m, the mass of the object, plus or minus, because we have two roots, 1 over 2m times the square root of c squared minus 4km. Okay, so this is the characteristic equation, and these are the roots of the characteristic equation. As we might expect, the solution for this displacement, okay, and the motion of this bob, or the motion of the spring mass system, depends on what? First, it depends on mass, as you can see here, and it depends on stiffness, damping, which is damping ratio. So we have mass, we have damping ratio, and we have K, the stiffness. So we have like 3 different major parameters that is controlling the motion of the spring mass system. We have the damping, so we call this C to be, it is representative of what? It is damping, okay? And M, of course we know it is the mass, okay? And K, it is what? The stiffness of the system, the stiffness of the spring itself. Okay, so we have damping, mass, stiffness. We have 3 different parameters that is going to control the motion of our system. Okay, and this is what I've written here, that we have mass, damping, and stiffness. They are going to control our case. Okay, very nice and very cool. And now let's go and put our first step in the journey of the unforced motion and how we are going to solve it. Okay, now case number 1 is going to be dealing with the main 3 parameters, okay, which is C, K, and M. Let's go back here. We have C, K, and M under the radical. Actually, as we said, the roots of the characteristic equation is going to be controlled by this radical. So this radical, it has the term under the radical, it has 3 different cases. Do you remember them? Case where that it is larger than 0 when it equals to 0, and it's smaller than 0, right? This is what we're going to deal actually every time. If it's larger than 0, okay, then it is going to be the first case for us, c squared minus 4km larger than 0. And we call this case overdamping case. Overdamping case. You are going to understand why we are telling it overdamping after going into this explanation now. Okay. Now the roots of the characteristic equation are real Do you remember this? Real and distinct. Please recall to the previous videos in this series and you are going to understand what is the meaning of real distinct roots for the equation. So we're going to have lambda 1 and we are going to have lambda 2. Lambda 1, we're going to have positive or plus here. Lambda 2, it is similar, but we have minus here, right? It is the same as the previous equation. For the characteristic or the two roots are the same, but one is positive, one is negative. The general solution of the spring equation in this case, okay, our spring equation, remember that our spring equation is what? Yes, this equation, okay, and equal to 0. We have 0 here in the right hand side. Okay, so now the general solution is going to be exactly y of t equals to c1e to lambda 1t plus c2e to lambda 2t. Very nice. That's right. I'm sure that you are familiar more than me even regarding this solution. Okay, you know this very well because we have two real distinct roots. So we are going to have e lambda 1t here and e to lambda 2t here. Okay. Now clearly we have lambda 2 is smaller than 0. Look here, lambda 2, it is smaller than 0. Why? Because C, M, and K, they are, all of them, they are positive because we have M and K, they are positive. M and K are positive, and under the radical, it is larger than 0. So this term is positive. Times 1 over 2m, and of course it is positive. So this term is going to be minus, it is negative. C, it is positive, M is positive, and we have minus here, so this means that the two terms are negative. Definitely they are negative. This means that they are less than 0. This is what we have said, that lambda 2 must be less than 0, right? So this means that c squared minus 4km must be equal to less than c squared. Definitely, because we have this is c squared minus 4km, it is larger than 0. This means that this term is less than only c squared, right? So the radical itself, the square root of the term is going to be less than c. Definitely, we just are taking the radical here and here. We are going to end up with this. So we are sure now okay, that lambda 2 is less than 0, and in this case lambda 1 is going to be less than 0 also. All right, look here, as we said, this term is going to be less than c. Okay, so and we are going to have here 1 over 2m times a term that is less than c, and we have here like as if we have 1 over 2m times c. So definitely this term is negative, this term is positive. This means that we are having lambda 1 must be what? Yes, negative. It is negative. This should be less than 0, right? And this is what we have said here. Okay, so now let's go to the next part. I want to clear this. Okay, so now we are sure that lambda 2 is 0, less than 0, and lambda 1 it is less than 0, as I said, because here we have this term, as I explained in the previous slide. Okay, so this means what? The limit of our function y of t, or our equation, equal to 0 when t reaches infinity. That's right, because lambda 1 and lambda 2, they are in the exponential of the exponential term here. So this means that they are going to vanish. This term and this term is going to vanish, right? Because e to lambda 1, it is, as we said, it is what? It is less than 0. So it is like minus, let's assume, for example, minus 10. So this is going to be very small. And at the end, we are going to, the function itself is going to tend to, sorry, this is when t, okay, tends to infinity. So we have t here. So if we have something like this means that we are having minus or negative term here. This means that the limit of y of t would equal to 0 in this case, right? Because it equals C1 1 over e lambda 1t plus C2 1 over e lambda 2t, right? This is our equation. Regardless of the initial condition, in that case, in the case that c squared minus 4km larger than 0, which is the overdamping case here, we call this is our case, the motion simply decays to 0 as time increases. This is what we want to say. So simply the motion decays to 0 as the time increases. That's the most important part. Okay, that's the most important part. This is called overdamping. Why it is overdamping? Because the motion decays, where that the damping is like controlling. So in this case we call it overdamping case. Let's see the graph here. Okay, this is similar to this our case. Let's have an example to understand what is the meaning of the word overdamping in a graphical form. Let's take some numbers here. Let's assume that we have c equal to 6, k equal to 5, and m equal to 1. It's clear that c squared minus 4km larger than 0, right? So based on these things we can have, or these values, we can have lambda 1 equal to minus 1 and lambda 2 equal to minus 5. Now the general solution is going to be c1 e to minus lambda 1t plus c2 e to lambda 2t, as we said, lambda 1 minus 1 and minus 5. Suppose the bulb was initially drawn upward 4 feet. This means that, suppose that if we have something like this and we have our the mass, if we assume that the mass here is what moved up, we moved it up here, okay, until it reaches here, was initially drawn upward 4 feet. So we have here this distance is going to be 4 feet, which is going to be y of 0 equal to minus 4. From the equilibrium, this was the equilibrium condition, and released downward with a speed. Speed means what? Yes, y prime of 2 feet per second. This means that y prime at the initial condition at 0 equals to what? 2. Yes, that's the case. So we have initial value problem here. We have initial value problem. So based on this initial value problem, we can solve and we can obtain our general solution to be y of t equals to, please check this by yourself also, because I'm sure that you can do it very well. So it is going to equal half e to minus t times minus 9 plus e to minus 4t. Okay, and let's have the first derivative of this. It is y prime of t equals to half e to minus t times 9 minus 5e to minus 4t. Okay. Okay, so this is the case. This is the case for us. I'm sorry, this is not y prime. I think there is a mistake here. This is, yes, I think that there is something here. So let me, this is the case. We have y of t and y prime of t. This is the values here. And then we can draw the relation here. Okay, we draw the relation. Take care, we start with 0 here, and then it goes down with, as we said, this is the case where that the bulb is being released, okay, at point 0. Okay, at point 0. We said that y of 0 was equal to minus 4, so it equals to minus 4, as you can see it here. And then here, when y prime of 0 equal to, this means that we are starting with the initial conditions for us here. The initial conditions, it is y of 0 equal to minus 4 and y prime of 0 equal to 2. So this is our initial condition. Okay. After that, when it goes with t, t is increasing. Okay, t is increasing. While that we are increasing t, can you look to this equation? We're going to find that the value is what? Decaying. It is decaying. And it never touches this equilibrium condition. We call this horizontal line as the equilibrium condition or the equilibrium position, right? So because we have the term here e2 minus t and we have e2 minus 4t, this means that we are going to reach to 0, but we are not going to reach it, never, because this is exponential form. It is not going to be, it won't vanish, but it would be very, very small. So this is the meaning of overdamping now. So this is the meaning of the overdamping, that our motion is going to go from minus 4, which is the initial condition, and decays until that it reaches to the initial condition. Actually, this is what will happen here, that when we have the system, this is the pop here, and we like move it upward, so it is going as if it is going to be like here, for example. We moved it up, so this is the difference, which is minus 4, and leave it. When we leave it, it will go down, 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 down until before, just before the equilibrium condition, it will stop. Okay, it will eventually, it is going to go to the equilibrium position after a great deal of t, after very long time. Okay, that's the meaning of this graph. Okay, now let's go to the next case, which is the case that we have where that c squared minus 4km it equals to 0. Okay, this is the second case, and in this case we call it the critical damping case. The critical damping case. In this case, the general solution of the spring equation is going to be like this: y of t equals to c1 plus c2t times e2 minus ct over 2m. Okay, this equation, you can solve it easily, and you are going to find that it has repeated roots. The characteristic equation has repeated roots, and if you can remember, this is the general solution in this repeated roots case. Y equal to c1 e2 minus ax over 2 plus c2x e2 minus ax over 2. This is the repeated roots case. So now let's go and look deeper into this equation. This case is called critical damping. Okay, we're going to see why it is critical damping. While y of t equal to 0, when t equal or reaches 0, y of t is going to 0. That's right. Imagine that this t here and t here is reaching infinity. This definitely would make our y of t equal to what? 0, right? Because we have the exponential form here. This would reach to 0. As with overdamping, now the bulb can pass through the critical point as the following example shows. Let's have an example here, and we're going to understand by numbers what is the meaning of this. Let's assume that the damping coefficient is going to be c equal to 2, stiffness and the mass going to be equal and equal to 1. It is very clear that c squared minus 4km under the radical, okay, they are going to be 0, right? So c squared, it is 4, minus 2km, it is also 4. So we are going, sorry, c squared minus 4km. As you can see, it is c squared minus 4km, it is going to be 0, okay? Okay. So in this case, we are going to find that the general solution, y of t, is going to be c1 plus c2t times e2 minus t. Okay. Suppose the bulb is initially pulled up for 4 feet above. So as we have done before, so supposedly it is, this is the bulb here, and we moved it up. Okay. So it is going to be something like this. Okay, this is 4, how much? 4 feet. So this is the difference here, 4 feet, okay, above the equilibrium position, and then push downward with the speed of 5. Then we're going to like give it a push downside with the speed of how much? 5 feet per second. This means that our initial value problem, initial conditions are going to be y of 0 equal minus 4 and y prime of 0 equal to 5. So in this case, y of t equals to minus 4 plus t times e to minus t in this case, based on the initial value problem and the parameters that we have here. Let's draw this relation. When we draw it, you're going to find this is y of t, the vertical axis is y of t, horizontal axis is t. And you're going to find that the initial condition here, we started with what? Y of 0 equal minus 4. At t almost equal to 0, they started from 2, but actually it could be like 0 here. So it is like minus 4. Minus 4, this is the initial condition. And y prime of 0, it is going to be 5. So here also it is the speed or the velocity is going to be 5. And then after if t is increasing, what will happen? Yes, there is decreasing because we have exponential function here. So it is exponentially decreasing and decaying until we reach to the point where that the pulp would exceed the equilibrium position, which is from at point 4. Look here, if we put t equal to 4 minus 4, it is 0. This means that our y of t, it is going to be 0 here. And then after t exceeding, then this term is going to be minus. So this means that we are going to here, look to here, at point y of 5, it equals to 0.007. So here it is almost 0.007. So this means that the bulb is going to reach this point and going a little bit after it. Okay, if we say this is the equilibrium position. Okay, and then we're going to find that at this point y prime of 5, this would equal to this term, which is 5 minus t times e to minus t. This means that it's almost like horizontal, and then we're going to find that with increase of t, that this value is going to decrease and we are going to reach 0 again in some way. So there is like as if there is some going and like going some a little bit above and then going back to the, sorry, it's not clear here, but anyway, this is the how it works. Okay, how it works, that there is some part will be in the other after the equilibrium position, and then after that it is going back again to the equilibrium condition. Okay, so this is actually what we want you to understand, that in the case of critically damping, okay, it will go, as you can see, cutting the equilibrium condition, and after that we are going to be, so as I said here, that the velocity y prime of t, okay, is negative for t, as I said, it is negative for t larger than 5. That's right. And it is going to be, the velocity increases, going to be positive for t smaller than 5 if you substitute here, right? So the pulp's velocity decreases after 5 seconds. After 5 seconds, you're going to find that what will happen? The velocity is decreasing. The velocity is decreasing. Okay, so this means that since the y of t, okay, is decreasing to 0 while t is reaching infinity, the bulb moves with decreasing velocity. The bulb is moving with decreasing velocity back toward the equilibrium position as time increases, right? That's what we want to highlight. Okay, so now this is the critical damping case. Now let's go to the next part, which is the third part, c squared minus 4km less than 0. We call this underdamping case. Underdamping case. Here the spring constant and mass of the bulb are sufficiently large that c squared less than 4km. The mass and the stiffness are larger than the damping term. This means that we are underdamping. Damping is not going to control here. And the damping is less dominant. That's right. This is called underdamping. We call this underdamping. The general underdamped solution has the form. This is the solution for our equation of motion. Y of t equal to e to minus ct over 2m times between brackets or parentheses c1 cosine beta t plus c2 sine beta t. Okay, this we are having a complex roots alpha plus or minus iota b. So we are going to find alpha equal to minus c over 2m and beta equal to 1 over 2m, the radical of 4km minus c squared. You can check it by yourself if you are having doubts. This kind of complex roots, it has this solution. Y of x equal to e to alpha x times c1 cosine beta x plus c2 sine beta x. Okay, so this is our solution, right? I think that you are very familiar with such type of equation. Okay, so what's the next? What we are going to do? Let's have an example. We're going to put c and k equal to 2, m equal to 1. If you calculate c squared minus 4km, it will be less than 0. And the general solution is going to be e to minus t c1 cosine t plus c2 sine t. Okay, so we are going to have the initial condition y of 0 minus 3. This means that the pulp is driven downward minus 3 and the velocity was 2. The solution in this case, based on this equation, is going to be minus e to minus t times 3 cosine t plus sine t. The behavior of this solution is visualized more easily if we write it in a phase angle. Actually, this is a form that we commonly use in mathematics and engineering in general in order to make our equation to be easy to be understood. Okay, I'm going to show it to you how now. So let's choose something like two constants, c and delta, such that this is what we call it the phase form. The phase form is like a constant multiplied by a kind of sinusoidal function, and here inside the sinusoidal function we have this delta, which is, we call it the phase angle. This is a very famous and easy to interpret kind of equation because c, it gives us the amplitude, and this angle, it gives us the phase angle. Okay, so this is very nice form for us. Okay, so in this case we are going to assume that our term, which is this term, okay, this form here, this between the parentheses, we want to change it only, okay, to this one. This is the same. Actually, we are going to form it or to change it to this form. We want it to equal to this form. Okay, we didn't do anything, just we are rephrasing the equation again. So we are going to claim that the right hand side, c cosine t plus delta, it equals to, from the trigonometry transformations, c cosine t plus delta, it is going to be cosine cosine minus sine sine. Do you remember this rule? So we're going to put c here, cosine t cosine delta minus c sine t sine delta. This is the right hand side. What about the left hand side? It is the same. 3 cosine t plus sine t, it is the same. Then look to the right hand side and the left hand side. We have here, I want to clear this actually here. So we have here in the first term it is cosine t, and the second term is sine t. If you look to the right hand side, you're going to find that we have cosine t, which is similar to this. This means that the two coefficients here, c and cosine delta, must equal to 3, right? And the second term on the left hand side, it's sine t. It must equal to this second term because it has sine t here. So this means that minus c times sine delta should equal to what? 1, right? This is what I'm going to write down in the next one. Okay, so this is what I said, that 3c cosine delta, c and cosine delta, they are going to be 3, which is similar to this term, and sine t, which has 1 here it must equal to minus c times sine delta. C sine delta equals to minus 1. It is the same, we put only the minus on the right hand side. So based on this, we want to get the delta actually, because delta, it is the main, C and delta are considered to me the main parameters that needs for our phase form. Okay, remember, let's go. We want for the phase form, we want what? C, parameter C, and delta, another parameter. So we are making some manipulation in order to get this C and delta. So now we can obtain delta because we have cosine delta here, we have sine delta here. By dividing, we can obtain tan delta. It is minus 1/3. This means that delta would equal to minus arctan 1/3. To solve for C now, the second parameter is C. Already delta is given, that delta already obtained. We want C now. This is the second. So go back here. We have cosine delta, which is known for us. We know delta now. So we can say that this is cosine delta. We know it. And we have 3 here. Then C can be obtained. Right? This is an easy issue. We can obtain it. Or we can put it like this. C squared cosine squared delta plus C squared sine squared delta equals to C, right? This is from the trigonometry transformation. You're going to find that cosine squared and sine squared is going to be 1, as I put it here. C squared times cosine squared delta plus sine squared delta. So this means that C squared would equal to 10, and then based on this, C would equal to the square root, C equal to the square root of 10. Okay. Anyway, you can find C easily. It's not a big deal. So now we know delta. Now for us, we know delta. It is okay. We know C. It is okay for us, right? We are having this C and we have this delta. So we can put this term only of the original equation. Remember, well, it is part of our general equation here. We didn't take the term, this term, only we are talking about this term only. We found C, we found delta. We can put it in our form now. Let's go and put it. So C is the square root of 10. Then our equation is going to be exactly cosine t minus arctan. This is what? This is delta. And this is square root, which is C, minus e to minus t. This is from the original equation, okay? This is from the original equation. Let's go back to the original equation. Yes, we have here minus e to minus t. Okay, so just we put it here. This is minus e minus et. And cosine t minus, this is delta and this is c. Okay, what is the point here? We want at the end to graph it. Look here. From this phase form, we can say many things. The graph is a cosine curve. Now it is very easy for us, cosine curve, to say it. And it is decaying by an exponential form. So we have a cosine curve here, and it is going to be enveloped by 2 envelopes. The first envelope is plus the square root of 10e to minus t, which is the term, multiplication term here, the exponential term here. And we have another envelope, which is the bottom envelope. Okay, the bottom envelope here. That's the case. Okay. So we have these 2 things right now. We have these 2 things right now, which is the 2 envelopes. Okay, we have the envelope. This is the upper envelope. This is the lower bound or lower envelope. At y of t equal to 0, where it will come, actually it will come when t, this t, is going to take this value. Okay, arctan 1/3 plus 2n plus 1 over 2 times pi, and this is n, which is going to be 0, 1, 2, 3, and so on. Okay, anyway, do not worry about this. If you go to this equation, you are going to find yourself, if we're talking about this equation, you are going to find yourself that having a cosine curve and enveloped by the decaying terms here, which is the exponential form, the exponential terms. Okay, so this is what I want to say, and this is why we call it, if you remember, we call it what? The underdamped. Underdamped means that our system here is underdamped, means that it is not, damping is not the dominant one. Okay, as we said here, that it is damping is less dominant. Okay, so in this case you are going to find that our damping is less dominant, but we have the equation of motion, or the motion graph, is like controlled by the sine cosine function. Okay, and at the end we're going to find that the bulb passes back and forth through the equilibrium points as t increases. So if this is the equilibrium point, okay, if we say this originally the equilibrium point, then you are going to find that in our case the bulb is going, say this is here, this line, equilibrium position. So actually the spring is going to stop here, and then it will go another time here, and then go another time to be here, and then go here. So it is going up and down. Okay, that's the meaning of it. When it will cross this equilibrium, when it will cross this, when n equal to 0 or 1 or 2 or 3 or 4 and so on, because we have this term here is based on pi. So at the point where n equal to 1, you are going to find that the object is going to be at the equilibrium condition. Then it go up, go down, go up, go down, go up, go down, and so on. Okay? Okay. Now let's go to the next part, and the next part of this video, which is related to the forced motion. Okay? We are going to talk about the forced motion. Forced motion means what? In the left-hand side, we are going to deal with the same equation, but in the right-hand side, we are going to find a forcing term. A forcing term. What is the forcing term means? That we have force. It is being applied on the system. Okay, so the system itself is not going to be only free, but we are going to apply f of t here. Sorry, we're going to apply f of t on the system that is going to control its motion. So we have forced motion here. This is why the word forced has been used. Why the term, or the why the word forced has been used. We have solved the associated homogeneous equation. This is the associated homogeneous equation. Remember that we are dealing with non-homogeneous equation, because the right hand side, it is what? Exactly. It is, there is a term here. So already we have solved this before, because we need to solve the associated homogeneous equation first, and then we need to search for a particular solution for the entire non-homogeneous equation, right? So we have solved the associated homogeneous equation in all cases on C and K, all cases that is larger than 0, less than 0, equal to 0, right? And M. For the general solution of equation, we need only a particular solution. Now this is our main problem now. We need a particular solution. Application of the method of undetermined coefficients yields the particular solution. Okay. So we are going to deal with undetermined coefficient. Okay, this is our way and our method for obtaining the particular solution. Okay, now let's go with the first case. As usual, we're going to have first case, overdamped forced motion, which is c squared minus 4km larger than 0. It is the same as before. Then let's have some values directly to make it easier for us to understand. We have C, damping coefficient equal to 6, stiffness factor equal to 5, M equal to 1, A equal to 6, radical 5, and omega, take care, omega, it is the forcing frequency. The forcing frequency. If the bulb released from rest from equilibrium position, then y of t satisfied the initial value problem. So we're going to have from this is the case where our bulb or our object is going to move from equilibrium. Nothing would happen. So y of 0 at t equal to 0, it was 0, and the velocity was 0. So it was nothing. It was under equilibrium. This is the initial conditions. The solution is that y of t for this one is going to be y1 plus y2 coming from the associated homogeneous equation. You understand them very well. This is covering this part. And the third term is going to be y particular, which is sine radical phi of t. This is y particular. You can obtain it from our indeterminate coefficient strategies that already we have explained before. Okay? Okay. Now let's discuss about this. As time increases, now let's go to the equation after the solution. We have like two terms here with the exponential function, and the third term with sine square root of 5 times t. As time increases, what will happen? The exponential terms decay to 0. So these two terms are going to decay, right? Because it is e to minus t and e to minus 5t. So they are going to decay. What is going to remain for us? Exactly. It is sine radical 5 times t. So it is going to be as if it's a sine. This is why it is sine. Sine and constant actually here. As you can see here, it is constant, almost constant, right? This means what? In the first, there was some decay, and after that, it is going to be constant as a sine curve, So this term is going to vanish after at the time where that t is going to reach to infinity. Okay? And the displacement behaves increasingly like sine radical phi of t oscillating up and down through the equilibrium point with approximate period of 2 pi over square root of 5. Okay, this is the period that we are dealing with. Anyway, this is how it works. So the bulb is going to up and down around or from the equilibrium position. Now let's go to the critically damped force motion. Critically damped. In this case, of course, you understand that c squared minus 4km equal to 0. Let's assume some values and let's work with these numerical values to make us understand how the critically damped force motion is working. We have c equal to t, m equal to k equal to 1, omega. The forcing frequency is 1 and A equal to 2. Assume that the bulb is released from rest from the equilibrium point. This means that we have exactly y, sorry for this. So we have y of 0 equal to y prime of 0 equal to 0. And this is the solution for our equation, which is y double prime plus 2y prime plus y equal to 2 cosine t. With this solution, we are going to find this is the solution for us. This is coming from the associated homogeneous equation. This is coming from the particular solution, okay? I'm not digging deeper on these topics because already we have explained it before in the previous videos, okay? So we are going to look to the figure in order to understand what is going to happen. But before going to the figure, in this case, you are going to find that as t increases, what will happen? The term with the exponential factor would what? Yes, decays. It will decay. Although not as fast as the overdamping case, the previous case, it's not very fast. Although not as fast as in the overdamping case, where there is no factor of t. Nevertheless, after sufficient time, the motion settles into nearly, but not exactly, okay, as a sinusoidal motion back and forth through the equilibrium point. Let's go and see. Yes, this is what will happen here. So here, let's go. We are talking about the critically damped. So we are talking about this graph, critically damped here. Okay. So look here. This is the previous one, which is overdamped. almost they are the same. This one almost like this, but the difference is, look how many peaks here, how many cycles here. We have 1, 2, 3, 4, almost 5, until t equal to 12 seconds, right? Look here. We have 1, 2, 3, 4 only at t equal 20. This means that here, as you can see, even that the amplitude is going to be the same, but it is only 3 cycles here, or 4 cycles here, many cycles, okay, in only like 10 or 12 seconds. But here it is going to reach this steady state case, okay, after what we can say after a little bit longer time, okay. But anyway, they are going to reach the steady state, okay. So the number of cycles here within 10 minutes, as you can see, or 20 minutes, it's only 4 cycles. Here within only, if we have 20, this may be like 10 cycles, okay. Okay, now let's go to the last part, which is the underdamped force motion. The underdamped force motion. Let us assume the underdamped means that c squared minus 4km, it is less than 0. And let's assume that c equal to k equal to 2 and m equal to 1, omega equal to square root of 2, and a equals to 2 square root of 2. So this definitely c squared minus 4km less than 0. Suppose the bob is released from the wrist at the equilibrium position, then this means that we are having exactly, these are our initial conditions. So the initial value problem is going to be, this is our equation, the non-homogeneous equation, as you can see here, this is our equation. And the solution for this non-homogeneous equation, undetermined coefficient, as we said, you can train yourself by making the solution and check whether that the book or this solution is right or wrong, okay? So this is a very good practice for you. You can, from this equation, try to solve it by yourself, okay? And find whether it's right or wrong. So let's go here. Look here that we have the exponential function here multiplied by sinusoidal function, and another term only sinusoidal function. Unlike overdamping and critical damping, the exponential term e to minus t has a trigonometric factor sign, trigonometry or trigonometric factor sign t. Okay, let's have, so the graph, as time increases, the term minus square root of 2 times e to minus t, this term, sine t, this term here, becomes less influential, and the motion settles nearly into oscillation back and forth through the equilibrium point with a period of nearly 2 pi over the radical of 2. Let us see this graph. This wording is very nice, but we can see the graph better for us. Okay, so here we have this term, and we have another term here. So as time increases, the term, this term, would be less influential. Means that it has effect on the motion, but it will be less influential when t increases. So if t is increasing here, this means that it is going to turn to be less influential, and the motion settles nearly into an oscillation back and forth through the equilibrium point with a period of nearly 2 pi over the square root of t. So we are having also this kind of steady state. So remember, well, that we are coming to a steady state, okay? Ultimately, we are coming into to a steady state. Okay, let's go to the last portion of this lecture or this video, which is related to resonance. In the absence of damping, okay, whenever that we do not have damping, an important phenomenon called resonance can occur. Suppose that c equal to 0. Look at this. This is a very important case, c equal to 0. But there is still a driving force that is being applied in the system, which is a cosine omega t. The spring equation in this case is going to be y double prime plus k over m times y. There is no y prime here because already we have c equal to 0, so the term already has been cancelled, okay, removed, omitted, because it is 0, okay. It equals to the right hand side here. As you can see, it is a over m cosine omega t, okay, a over m cosine omega t. So now this spring equation has general solution using the undetermined coefficient, okay. This is the long one here. You can see this is y1, this is y2, this is y prime. Remember well this equation, as you can see here, we have omega, and we here find something called omega node, okay. What is the difference between omega and omega node? Actually, omega here, this is the forcing frequency, which is related to the force itself, okay. This is related to the force. But whenever that we're talking about omega node, it is related to the system itself, and it equals to the stiffness of the system over the mass of the system. So this is the difference between omega and omega node. In our solution, we are assuming that omega node does not equal to omega. That's very important, okay? So that we are going to have a solution for this. So in which omega node equal to the square root of the radical of k over m. This number is called the natural frequency. This is what we call it, natural frequency of the spring system, and it is a function of the stiffness of the spring and the mass of the bulb. And omega only, without any subscript, is the input frequency and is contained in the driving force, as we said here and mentioned here. This general solution assumes that the natural and input frequencies are different. Yes, this solution assumes that these two frequencies are not the same, because we are going to study the case where that they are going to be the same, and at this particular case frequency will occur, okay. Of course, the closer we choose the natural and input frequencies, the larger the amplitude of the cosine omega t term in the solution. That's true, right? So take care that this is in the denominator. So whenever that they are closer together, this means that we are approaching 0. And 0 in the denominator means that this term is going to be dominant. Okay, take care. Okay. Now the case that resonance occurs when the natural and input frequencies are the same. That's the point. So they are the same and there is no damping. Now the differential equation comes to be the same. The left hand side is the same as before, equals to a over m cosine omega node t. So the equation, first we need to obtain, yes, let's assume that actually here we need to derive another type of solution, because here we are assuming that omega node equals to omega. So we are going to derive a solution for this case. Okay, remember here it was omega node does not equal to omega. Here we are going to say that, already we say that omega equal to omega node. Okay, this is our case. Okay, let's obtain the solution for the equation starting with the homogeneous differential equation. The left hand side equated with 0, as you can see here, equated with 0. Okay, this k over m, as I said to you, it is going to be related to the natural frequency of the system, which equals to the square root of k over m. This has the general solution. This is, you know it, constant coefficients, so it is going to be c cosine omega t plus c2 sine omega t. Omega node, I'm talking about omega node, take care. Okay, not the forcing frequency, it is the natural frequency. Okay, so we obtained the homogeneous equation. Let's go to the non-homogeneous equation to find y particular. Okay, so now the particular solution, this is the equation here. We are going to use the undetermined coefficient, and we are going to assume A cosine omega naught t plus B sine omega naught t. But, however, these are solutions of the associated homogeneous equation. So instead, we are going to use another way because it is a solution for the homogeneous equation. So it will not work for us, this assumption. We need to assume another thing. Y particular is going to be AT, we multiplied by t here, and we multiplied by another t here. So instead of B sine and A cosine, it is AT cosine and BT sine, okay? Substitute the particular equation into equation 2.4, which is this equation, to get, this is the equation that we're going to have. Minus 2A omega naught sine omega naught t plus 2B cosine omega naught t equals to A over m cosine omega naught t. Now, this is a kind of particular solution, so we can assume anything for A and B, okay? We can assume anything for them. It is arbitrarily chosen, okay? We can do anything with them. We can use anything for... So we are going to choose A to be 0, and let's see what is the corresponding B in this case. So this is what we have done, that we put A equal to 0, and 2B cosine omega naught t would equal to A over m cosine omega naught t from here. Okay? So that's the, that's if we put A equal to 0, so this term is going to vanish, and then 2B cosine omega naught t equal to this term. So cosine omega naught t cancels cosine omega naught 2, and A over m would equal to 2b, okay, 2b omega. 2b omega naught equal to 1 A over m. Okay, so let's have this. Okay, I think that there is something here. There should omega naught. I think it should be here. And if we assume A equal to 0, then we are going to find that T2b omega naught equal to A over m. This gives us the particular solution, which is Yp of t equals to A over 2m omega naught t sine omega naught t. This is our particular solution here, okay? Y of p, okay? Y of p, which is the particular solution. Then we can obtain it easily after having these values for A and 2b omega naught. So the general solution in this case is going to be y of t equal to y1 here, y2 here, y particular here. So we have c1 cosine omega naught t plus c2 sine omega naught t plus this y particular, we put it here. Remember well that we are talking with omega naught does not equal to omega. Okay, now what will happen for this equation? Look here, there is something unique for this equation. It has t outside. T is outside. This means what? This is very unique actually here. In case of resonance, what will happen is for this equation, everything is okay. It is sinusoidal functions everywhere, but we have t outside of the sine or cosine. So we have t outside. This makes a problem for us. This means that with the increase of t, what will happen is the response is going to, exactly, it is going to be increased, as you can see, in this way. What is this? It is a kind of, this is what we call it resonance, that the response of the spring is going to be moved higher and higher and higher and higher until that it would collapse. That's the problem, that this t outside, this makes the problem. This makes the problem for us, okay? So this is an example for this graph, which is C1 equal to C2 equal to omega 1 equal to 1 and A over 2m equal to 1. Now this is the solution for this particular values of C1 and C2 and so on. So we're going to find that it is really increasing without a limit. This is what makes the resonance. Now I'm going to give some hints about these, the importance of resonance. So while there is always some damping in the real world, if the damping constant is close to 0 when compared to other factors, and if the natural and input frequencies are nearly equal, so these are the two conditions. damping is 0, and natural and input frequencies are equal. Then oscillations can build up to a sufficiently large amplitude to cause resonance-like behavior, which, as I said to you, that is going to the motion is going to increase and so on. This caused the collapse of the Broughton Bridge near Manchester in England in 1831. Can you imagine that it was a main cause, the main root cause for the collapse of Broughton Bridge in Manchester in England? Okay, when a column of soldiers marching across maintained a cadence input frequency that happened to closely match the natural frequency of the material of the bridge. Then the bridge collapsed. Another important case happened in Tucumanero Bridge, a very famous bridge failure happened in 1940 in the United States, and it was due to the resonance as well. You're going to see, if you search on the, I will put a supplemental video on the iCampus for this. You're going to see the Tucumanero Bridge failure video clip, and if you want also you can watch it on YouTube if you Google it or if you search for this. Okay, I hope that you understand this well. I'm going to give you now a home assignment. This home assignment actually I think it will be easy for you, and it's part of our calculation. So actually this is the main equation that we have used. It's non-homogeneous equation for our spring mass system. So using the undetermined coefficient, get the particular solution of the following. I want you to get the particular solution and compare it with this value. Okay, I mean that with this answer. Check if the following is correct answer or not. If it is not the correct answer, write your answer. So this is what is written. Y particular equal to this. You need to derive the particular solution and check it with this, if this is correct or not. If it's not correct, then write down your correct answer. Okay, so this is the homework for today, and this is related to the spring mass system. Thank you, and see you in the next video.